Welcome to the course on Advanced Power Electronics. So we have a second lecture today on power semiconductor devices with outline of introduction, power semiconductor devices, application based of various converters, configuration, introduction to bandgap devices, silicon carbide and GaN devices, and fundamental properties, Schottky rectifiers, and silicon carbide planar MOSFET, power MOSFETs, and silicon carbide IGBT, commercial GaN power-based electronic system, and references. So coming to introduction, until 1970, the conventional thyristor have been extensively used for power control in industrial application, and since 1917, various type of power semiconductor devices were developed and became commercially available. And the diodes are made of only one p-n junction, where the transistor have two p-n junction and thyristor have three p-n junction. As the technology grows and power electronics finds more applications, the new power devices with the high temperature capability and low losses are still being developed. And the earlier devices were made of silicon material, and new devices are made of silicon carbide. So gallium nitride and silicon carbide are enabling higher level of power density and efficiency compared to the traditional silicon metal oxide semiconductor. So the commercialization of bandgap devices such as GaN and SiC has changed the landscape of electronics industry once again, and these devices offer a substantial improvement over both MOSFET and IGBT, including low gate capacitance to enable faster turn off and turn on, and while reducing the gate drive losses. And these devices also offer significant lower output capacitance, enabling designer to achieve high switching devices without an increase in associated switching loss, and to shrink the size and weight of magnetics in the system. So all of these high voltage devices have distinct characteristics, and as shown in figure 1, each have a different power level and switching frequency. As you can see, like MOSFET we go to like 100 kHz, and IGBT we go typically 10 to 15 kHz, and silicon carbide we go typically 120 kHz, and GaN devices we go even more than 10 MHz. So this is the classification of power semiconductor devices, starting power semiconductor silicon and silicon carbide, and it has a different devices like a typically short diode, safety diode, external diode, double diffuse diode, then transistor, bipolar transistor, NPN, PNP, MOSFET, and IGBT. Similarly, the thyristor, we have a thyristor for phase control, part thyristor, GTO, then IGCT, then MCT, MTO, and then of course silicon carbide diode and transistor, and then MOSFET, shorty diodes, and JVS diode and pin diode. And the power range of commercial available power semiconductor devices, as you can see in the diagrams, it goes to up to 10 power 4 up to 10 kiloampere. So we can just see, the power MOSFETs are available up to typically up to 1 kiloampere, but on low voltage. High voltage, of course, they are only available up to 100 ampere. Then your IGBT, which goes up to typically 2.5 kiloampere, of course, up to volts around 6.5 kilovolt. Similarly, for thyristor, it goes 12 kilovolt to typically current rating of around 5 kiloampere. And then GTO up to 6 kiloampere up to 6 kilovolt. So these are typically from different manufacturers, either UPEC, Mississippi, UPEC, ABB, Mississippi. Those are the manufacturer of these leading components. Like then power versus frequency. Of course, you can see the power up to go to 10 megawatt, and frequency up to 1 megahertz, with the starting with thyristor on low frequency up to typically 100 Hz, then GTO, then IGCT and IGBT. Then of course the MOSFET goes to high frequency. So now coming to device choices for high power application, from AC 50 Hz to 60 Hz main supply, the phase control and bidirectional thyristor are most economical devices, and cool MOS and IGBT are the potential replacement for MOSFET and BJT respectively, low and medium power application, and GTO and IGCT are most suited for high power applications requiring force computation. And with the continuous advancement in technology, IGBTs are increasing employed in high power applications, and MCTs may find potential applications that require bidirectional blocking voltage. And this is typically device choices for different power level, starting typically from your power usage. MOSFETs are from up to 2 kilowatt, then medium MOSFET IGBT up to 500 kilowatt, and then high power IGBT, IGCT, and thyristor are used typically above 500 kilowatt for different applications, as it is given here. Like we already talked about in first lecture reasonably for applications. So coming to power diode, we have a typically PN diode as symbol shows, and how the characteristic. So we have a ideal, if you look at ideal characteristic, in forward we must have a 0 voltage drop, and in in backward we should have a zero current flowing into, but practically you can see the characteristic here. It takes a small drop and forward it conduct, and in reverse direction to has a leakage current up to certain voltage. After that we have a breakdown. So we never operate up to the breakdown, we operate well safe limit of this diode. And this is typically of course the reverse recovery and soft recovery of the diode and abrupt recovery of this diode, while going to be turned off. And now the power diodes of type, depending upon the recovery characteristic and manufacturing technique, the power diodes can be classified into categories: standard and general purpose diode, fast recovery diode, and Schottky diodes. As you can see the symbolic difference in all three. Then silicon carbide diode, which is new one. You can see how silicon diode and silicon carbide diode have a reverse recovery current reduction like anything. So silicon carbide is a numerical power electronics and physical property conform to silicon and granite by power, and they have the following: no reverse recovery time, ultra fast switching behavior, and no temperature influence on the switching behavior. So now coming to silicon carbide Schottky diode. So Schottky diodes are used primarily in high frequency and fast switching applications, and many metals can create Schottky barriers on each silicon or germanium arsenide semiconductor. And silicon carbide Schottky diodes have the following features: lower switching losses due to low reverse recovery charge, fully surge current stable, and high reliability and ruggedness, and low system cost due to the reduced cooling requirement, high frequency design, and increased power density solutions. So you can just see how the basic internal structure of the Schottky diode, how it's represented in the symbol like. Now coming to power transistor have control turn on and turn off characteristic, and the transistor which are used in switching elements are operated in saturation region when it is turned on, resulting in low on state voltage drop even less than the diode. And the switching speed of modern transistor is much higher than that of thyristor, and they are extensively deployed in DCDC and ADCH converter with the inverse parallel connected diodes to provide the bidirectional current flow. It cannot have a reverse voltage blocking capability. The power transistor can be classified broadly into 5 categories: metal oxide semiconductor transistors like MOSFET, then cool MOS, bipolar transistors BJT, and insulator gate battery transistor, and static induction transistor. Coming to power MOSFET, a power MOSFET is a voltage control device and requires only a small input current, and the switching speed is very high, and the switching time are of order of nanoseconds. And power MOSFET finds increasing application in low power, high frequency converters, and MOSFET do not have the problem of second breakdown phenomena and do BJT. However, MOSFETs have the problems of electron static discharge and require special care in handling. In addition, it is really difficult to protect them under short circuit fault condition. And you can see how the symbol for different ring MOSFETs, from semicron as well as internal rectifier look like. So you can just see basic physics of how it is a power MOSFETs, the depletion type MOSFET and enhanced type of MOSFET. And then typically parasitic model of the enhancement of MOSFET like parasitic bipolar, then the internal diode, how it is really configured, and then the MOSFET with the actual diode. So coming to like a steady state characteristic of power MOSFET, the MOSFETs are voltage control device and have a very high input impedance. The gate draws a very small leakage current on the order of nanoampere, and the current gain, which is the ratio of the drain current to ID to the input gate current, typically order of more than 100. However, the current gain is not an important parameter. The time conductance, which is the ratio of drain current to the gate voltage, define the transfer characteristic and is very important parameter. And these are the steady state characteristics for N channel and P channel depletion kind of MOSFET and NS kind of MOSFET of N channel and P channel, and how your IDVD characteristic of this with different gate voltage, of this characteristic of enhancement type of MOSFET. So coming to switching waveform timings, how it really goes as if you give a gate pulse of order of, as you can see in the top, how really the voltage typically, VGS goes and how the current builds up like. So why even if it is a small current during, you can say, switching turning on, turning off, it has a high losses because of multiplication of voltage and current like. Coming to now BJT, bipolar junction transistor. A bipolar junction formed by adding a second PN or N region to the PN junction diode with two N region and one P region. Two junctions are formed and it is known as NPN transistor, which is widely used. And with two P region and one N region, it is known as PNP transistor. And you can see the configuration of NPN and PNP transistors. Like both are used, but NPN is more preferred for power application. Like for NPN, the emitter N layer is made wide with the P base as a narrow, as you can see in the diagram on the left side, and the collector side N layer is narrow with the heavy dop. And for PNP, the emitter P layer is made wide and the N base is narrow and the collector side is planar is narrow. So how physically looks like typically, I mean as a size, you can have a different, like how emitter is there, how the collector is there, how the base is there, and how the steady state characteristic typically with the base current and as well as the typically, so it will typically go to, we operate normally in such phases, so it is, I mean, and of course our cutoff region with the no current into that, so cutoff region saturation are shown. If it goes into active region, then certain device will blow. The reason being it has a large voltage across it and large current, so it means losses will be very extensively. Provided you remove the heat loss of that, which are used in normally in linear power supplies for low power rating. Otherwise, we operate in saturation, typically having a very voltage, small voltage drop, and even for large current, or in cutoff where no current flow through it. And of course, you can see how the transfer characteristic is there of the base and collector VC voltage as a voltage gain. And now you can see how the typically the switching characteristic of this on, turning off looks like, how the current builds up applying the base current. Here this device is the current operated device, so base current decides typically here, so how the collector current increases and decreases on turning off. So it's a volt level operated device, because if you give the base current, then only the device will be coming into conduction and turning remain on. Now coming to IGBT, which is really a very wide voltage range device nowadays and preferred. It has the advantage of IGBT as well as the MOSFET, and as you see, equivalent circuit is a combination of MOSFET and IGBT. I mean, what was the drawback of this? Your BJT, it is removed, I mean, by the MOSFET on the input side. So IGBT combines the advantage of BJT and MOSFET, and IGBT has a high input impedance like a MOSFET and low on-conduction losses like BJT, even much lower than we have a better device. However, there is no second breakdown problem as with the BJT. So by chip design, the structure, the equivalent drain to source resistance RDS is controlled to behave like that as a BJT, as you can see in the simplified circuit and equivalent circuit. Now output characteristic and transfer characteristic of this, you can just see typically how it looks like. So you can just see here, I mean, how it is really, you get the collector current with the collector emitter voltage, I mean, coming to in kind of saturation here with the applied gate to emitter voltage as a voltage operated device, and then how the collector and gate emitter voltage characteristic is there. And these are of course the operating quadrant of transistor with diodes. Like you can use the different kind of application, either simple the diode, then MOSFET with two external diodes, then BJT with the kind of with the anti-parallel diodes and the BJT. And then the series diode used for, of course, the purpose of series diode to take reverse voltage blocking capability if you use it in current source converter. Then as a two anti-parallel switch to operate as a, you can call it this as a switch, as a bipolar switch, and then the next as a two different kind of, I mean, configuration with the bipolar as well as a switch to operate with the four diodes with a single BJT. So these are, of course, so many variations are there that these are used for as a different switch for different purposes in power electronics applications. Like coming to bandgap devices like a silicon carbide and GaN devices. So the fundamental properties, the basic material property of the relevance of power electronic devices are the energy band gap and the impact ionization coefficient and the electric coefficient, the thermal conductivity and the electron affinity and the carrier mobility. So you can just see in silicon germanium nitride and you can call it the silicon carbide, how these are really the band gap changes, as well as typically the thermal conductivity, relative dielectric, electron affinity and density, and the density state velocity changes of fundamental properties, like which make these GaN devices much better than typically even from the silicon, I mean, because of these different properties. Like coming to energy fundamental properties, energy gap, the gallium nitride and silicon carbide have a energy band gap that is much larger than that of silicon align. Their classification as a band gap semiconductor devices. Energy band gap of semiconductor decreases the increasing temperature due to thermal expansion of lattice As you can see here, the typical characteristic of energy band gap in electron volt with the temperature. So even the high temperature does not affect too much of all this. And a semi-empirical formula for change in band gap to silicon with temperature is written as equal to 1.69 minus 4.9 10 power minus 4 T square T plus 65, where T is absolute temperature in Kelvin. Similarly, temperature dependence of band gap devices is 3.51 into 9.10 power minus T square T plus 1840. So you can just say they can withstand with the high temperature both GaN devices as well as silicon carbide compared to the silicon device. Now breakdown voltage, you can just see the band because of band gap and dielectric coefficient, how electric background goes. So they can certainly have electric background field quite large with new devices. Even it can go diamond by type, but that's very costly. But GaN devices is 2 kilo volt, and typically your so different kind of devices, how they can have a large band gap voltage. And then diff layer, so how it goes the diff layer typically, with the band gap and dielectric coefficient and diff layer. And so these are the property of which make the difference and all these. Of course, there is extreme diamond, but of course, we normally prefer to use the GaN devices and silicon carbide devices at the moment, which are commercially available at much cost-effective way. And day by day, costs are reducing of this. And then diff layer for on state devices, how your RDs, typically RDS on goes low for the silicon carbide and GaN devices, like when it conducts, like even for very high voltage, these devices have gone. Even a silicon carbide are not available even less than 700 volt. So they are made for basically for high power application. And then thermal conductivity. So their thermal conductivity also, you can call it like, especially silicon carbide is quite high compared to silicon. Of course, germanium is not so high, but the germanium nitride has a quite high, like 1.0 much comparable to silicon carbide, but your silicon, compared to silicon, but silicon carbide have a much higher, you can call it the thermal conductivity. That may also make typically that you can operate the device very efficiently, like better heat dissipation. And then the fast switching speed, you can just see how it is GaN devices, how silicon carbide, and how your silicon devices operate. So you can just see, the current quenching or turn off goes how fast typically. So that makes the device to operate high. You can call it high frequency and low losses even during the turning on, turning off process. Like, and then high temperature operation. These new devices, even like a silicon carbide, they can go compared to silicon much higher temperature also. As you can see, compared to the silicon, and power density is also quite high for these because of the less losses, like also, and RDS on also typically low in that case. So coming to Schottky rectifier, the main advantage of the band gap semiconductor for power device application is that they are very low resistance for the dip region, even when the design to support large voltage, and this favors the development of high voltage unipolar devices which have much superior switching speed and than the bipolar structure. And Schottky rectifier found by making a rectifying contact between the metal and the semiconductor drift region is an attractive unipolar device for power application. In case of silicon, the maximum breakdown voltage of Schottky rectifier has been limited by increase in the resistance of the drift region. The much lower resistance of drift region for silicon carbide and gallium nitride enables development of such Schottky rectifier with very high breakdown voltage. And the typical Schottky rectifier structure, how it looks like, and drift region with the substrate and cathode, and how the typically the field distribution typically, and how the saturation characteristic of Schottky rectifier, you can just see a different with the silicon carbide and germanium, how it is changed to. Then on state characteristic of these three silicon, and which makes the difference in the two. So you can say you can have a forward current density much higher in case of the germanium and silicon compared to the silicon carbide compared to silicon. That makes the typically these characteristic much better. And then the Schottky rectifier structure, reverse blocking. So coming to like silicon carbide planar power MOSFET. So in silicon power MOSFET, the on resistance becomes dominated by resistance of the drift region when the breakdown voltage exceeds 200 volt, and a high breakdown voltage, the specific on resistance of the device become greater than 0.1 ohm centimeter square, leading to an on state voltage of more than 1 volt, at typical on state current density of 100 ampere centimeter square. And for this region, the insulated IGBT was developed in 1980 to severe medium and high power applications, and superior performance of IGBT in high voltage application relegated the silicon MOSFET to application with wide operating for below 100 volt. and novel silicon structure that utilize the charge coupling concept have allowed expanding the breakdown voltage of silicon power MOSFET to 600 volt range. However, their specific conditions is still quite high, limiting to their high operating frequency while still switching loss dominate. So in principle, the much lower resistance of the drift region in silicon carbide should enable diode development of power MOSFET in very high breakdown voltage. You can see here with the basic concept how it is really changed, and how you can just have your own resistance calculation for as well as your specific capacitance calculation, like then the on resistance calculation totally, and then your regional resistance, drift region spreading resistance, the total contributing and substrate resistance, like, and then how the characteristic with the channel length and specific on resistance changes with. So in silicon power MOSFET, the on resistance becomes dominated by the resistance of the drift region when the breakdown voltage exceeds 200 volt, and a high breakdown voltage specific on resistance for device becomes greater than 0.1 ohm centimeter square, leading to the on voltage of more than 1 volt, typically 100. For this reason, the IGBT was developed in 1980, and the superior of IGBT application and novel structure. So now the placement of your bipolar silicon device in unipolar SiC was proposed to reduce the on voltage drop and switching loss in power electronics. Once the cost of a silicon carbide wafers and fabrication technology decreases sufficiently, these devices will replace the silicon IGBT for blocking of voltage 6 kV. However, for even greater blocking voltage, the specific on resistance for even your 4H SiC unipolar transistor became large, creating high on resistance power losses. This has motivated the development of IGBT using 4H SiC material. As in case of silicon IGBT, it is possible to make both channel P channel IGBT using 4H SiC, and this is typically how SiC IGBT with the different kind of regions are there with the emitter, then gate, then the shielding region, JFET region, N drain, N bus, NP collector, and collector, and then the characteristic of high level lifetime in microsecond and the on state voltage drop. And these are the different commercially available devices of silicon carbide, germanium carbide, germanium nitride from different manufacturers like Infineon, and if you look into ST Microelectronics, the different industry, of course, in different voltage ranges, starting 650 volt and up 1200 volt. So you can see these devices are not available even less than 650 volt, and their RDS on are in milliohm, and with their different currents and the charge on capacitance, and total write time, file time, all the characteristics you can see here as a quick look. And then commercial base GN for radio frequency device market size forecasted from 2080 to 24, like how it has gone typically in, starting from typically up to $1 million, like, and then typically commercial power level of this current future development, how it really expected to go in different kind of devices, like, and commercial then device. So how it is 1000 bidirectional DC-DC converter developed by Diamond Electric manufacturer, how it look like, compared to the, you can say, pan, how this total converter, of GaN based 1 kilowatt isolated bidirectional DC converter developed by Diamond look like by 2020 power electronics world, like, and the specification are given here, like, and typically 500 watt AC to DC converter, how it look like here. Efficiency here, efficiency is 92%, and typically here is efficiency up to 95%. Then the ultra high frequency, high efficiency AC power conversion module developed by AVX here, how it look like. And then 3 kilovolt AC DC power supply developed Bell power supply, how the size look like, and with the efficiency of 94% using this GaN devices. And then the typical 3 kilovolt AC DC rectifier developed by Altec, here also 97.8% efficiency, and the power density 33 watt per inch cube. Then the 3 kilovolt solar inverter battery charger developed by Henry, this with the efficiency of 98%. Then the 1600 watt computer power supply unit developed by Corsair, and with the efficiency order of typically different voltage range, and then the 40 watt USB type C power delivery charger with a specification of 45 watt voltage varying from 100 to 240 volt. You can use in North America or India, it's 50 to 60 hertz in case of your laptop or so. Then the property 60 watt GaN device smartphone charger. Then the property of 65 GaN device is smartphone charger by Optio for different applications. So these are the some application current and feature field interest of GaN and silicon carbide devices, starting from silicon domain 2, and then for wind power, smart grid, train traction application, PV inverters, hybrid electric vehicle, then in your industrial motor control, domestic appliances, and PC and smartphone and data centers. So this is gallium, silicon carbide and gallium devices are going to be really make a revolution in all these applications. To conclude, silicon carbide and GaN devices serve different voltage, power and application need, but they also overlap in some end equipment. And silicon carbide devices offer voltage level at as a 1200 volt with a high current carrying capability. This makes them a good fit for applications such as automotive and locomotive traction inverter, high power solar pumps, and large three-phase grid converter. On the other hand, with their superior FEM, inherent manufacture and cost advantage, and ability to switch at much higher frequency, can have become a device of choice for many designers in less than 10 kilowatt applications. So whether the product is USB Type C adapter or multi-kilowatt telecom rectifier and integrated robotics drive, the electric vehicle onboard charger designer finally have tools that enables them to make the best choice while designing the greener, lighter and more cost-effective product. And of course, key highlights are large forward and reverse producing, small leakage current, high on stored current, a small voltage drop, fast switching, short turn on top, small power control, large input with this kind of high voltage and high current during switching, good safe operating area, and positive temperature coefficient and on state resistance, large EV by DT and large DI by DT rating. Now coming to numerical problems. So first numerical solved problem is the bipolar transistor is 552 BF in the range of 8 to 40. The load resistance is RC equal to 11 ohm. Thus the DC supply 200 volt and the input voltage base volt is 10 volt. So if we see to saturation 1 volt and we E to saturation 1.5, the value of RB that result in a saturation on DF of 5 and the B force and the power loss PT in the transistor. As you can see the circuit here. So VCC 200 volt, all data are given. So overdrive factor is IB upon IBS. So IB is here 5 into 200, so that comes 11.3125, and required value of RB is BB minus BB saturation IB, that comes to 0.7514 ohm. And typically B force will be ICS upon IB, so it comes 1.6 ohm, putting the value, and PT equal to B plus PCC, so it's 35.07 watt. Coming to second, maximum junction temperature of Tj equal to 150 degrees Celsius and the ambient temperature of T equal to 25 degrees Celsius. Thermal impedance are 0.4 centigrade per watt and RCS is 0.1 centigrade per watt and RSA 0.5 centigrade per watt. Calculate the maximum power dissipation and the case temperature. So ATJ minus TA equal to PT in RJ plus RCS plus RCA. So putting the value, it comes here 100 degrees Celsius and the pitch gives the maximum power dissipation of 125 watt. Coming to third numerical, two MOSFET that are connected in parallel carry a total current of IT equal to 20 ampere. The drain source voltage MOSFET is I1 equal to VDS 2.5 volt and the MOSFET 2 is VDS to 3 volt. Determine the drain current of each transistor and difference in current sharing of the resistance are S1.3, RS2.2, RS1 equal to 1. So you can see the circuit how transistors are connected in parallel with the different resistance. So here you can call it ID1 plus ID2 equal to IT and VDS plus IDVS equal to, so ID1 you can calculate, it comes 9 ampere, takes about 45%, and then ID is equal to ID, the total current minus ID1, so 55, and delta ID 55 minus 45, 10%, and ID typically in B case, so you can call it ID, putting the value, it comes 10.5, and ID2 comes 9.5, so then the difference is only 5% difference in that. Coming to numerical power, current through the diode is shown in figure. Determine the RMS current, average diode current. If T1 is 100 microsecond, T2 is 350 micro, T3 500 micro, F250, FIC 5 kilowatts, and IM equal to 450, and I equal to. So you can just see how it look like your typically the current I1 and I2. Calculation of RMS current ID equal to, just keep the formula. So you will get around this ID1 equal to 50.31 and ID RMS value 29, and substituting the value total RMS will is come 58.09, and then average you get of both ID equal to typically 12.79. Coming to numerical problem, a 3-phase bridge rectifier supplying a highly inductive load at that average current of 60 ampere, ripple is negligible. Determine the rating of diodes if line to neutral voltage is your 120 volt 60 hertz. You can just see how the different currents in different devices are there, and then you can find out current through the diodes are shown. So here ID equal to 60 by 3, that's average. RMS current will be IR, putting the formula, it's ID by root 3, that's 34.64, and the PI in root 3 PM, so it comes to 294. Numerical problem 6, in quasi square wave 120 degree pulse width, the current I is 100 ampere, and calculate the correct factor, distortion factor, and total harmonic distortion factor. So current here you can see the waveform how it look like, and the current is 100 ampere. So you can find out fundamental 2 root 2 upon pi into sine 120 by 2. So it comes typically 0.79, and the RMS comes to RMS root 3 by 3 I, that comes 0.8165 I. So you can find out the crest factor from here 1.255, and distortion factor I1 upon 0.945, and total harmonic distortion, putting the value, it comes 31.0. Now coming to a single phase 7th numerical, single phase fully controlled base converter, supplied from 220 volt 50 hertz and pi angle 60 degree. Consider continuous load current of 10 ampere. Compute total harmonic distortion, current distortion index of mains current, and total demand distortion, endpoint distortion factor, displacement. So you have a thyristor converter with square wave current. Output, you have a quasi square current with the phase shift of alpha degree. So here you have given all data. So TAD will be up calculating from RMS and fundamental. So it comes 48 current, distortion factor comes around 40. Typically distortion index factor comes your TAD upon 1 plus TAD square, so it comes 43.59, and total demand distortion factor current, this so it comes around 48.43. And then the distortion factor TF1 1 upon TAD, so 0.9, and distortion factor displacement factor cos theta 1, that's cos alpha equal to 0.5, and power factor ABF into DF, that comes 0.4. Coming to question number 8, a single phase AC voltage control shown here is used to control the heating of packaging element in food vending machine. A power of 100 watt at 10 volt from the single phase AC mains of 230 volt. Feeder conductor have resistance 0.2 ohm. Calculate the AC RMS current, losses in distribution system. If ideal compensator is used to compensate power factor unit, then the AC source RMS current, losses in distribution, and ratio of distribution factor. So you are just getting 10 volt by controlling phase 10 volt RMS in the output, the phase control, and you can see it will be only conducting for very short period. So will have a certainly for short period very large current. So you have a load resistance and power voltage is given. So you can just calculate the load resistance 1 ohm, and the RMS voltage across the load will be IS into RL 10 volt, and supply RMS current will be IS under root P upon RL, that is 10 ohm. Losses in the distribution system because resistance is given. So two conductors, 2 IS square RS, that's a 2 and 10 square 0.2 40 watt, and after compensation power factor is unity, and the current becomes sinusoidal. So RMS supply current is your IC upon VS, so 100 upon 230, that is 0.15, and losses in distribution system, now current is reduced to 0.435 ampere, so 2 into 0.4 into 0.2, it becomes 0.76, and the loss ratio is 400 divided by 0, it's 529, and it means the such nonlinear load cause increased losses in the distribution system may hold much time as 529 times. Coming to question number 9, a 3-phase 40 volt 50 hertz 12 plus thyristor converter drawing a 400 ampere DC current at 30 degree firing angle of its thyristor. It consists of a transformer with a single primary star connected winding and 2 secondary windings connected in star and delta with the same line voltage transfer to provide 30 degree phase between the two sets of 3-phase output relay. Two 6 pulse thyristor which are connected in series to 12 pulse series. Design a AC tuned passive filter for the to compensate reactive power of 11, 13 and 23, 25. So you can just first calculate what is the IS1 from DC link current. It comes 623 and total reactive power 3 into VPH IS1 sin alpha. So it comes to 37.59 kVAr, and total, because 4 filters are there, so total capacitors are 4. So you can have a Q equal to 3 omega CV square. And from this you can find out the total capacitance 3.909 millifarad. and capacitor per filter by 4 is a 977.4 microfarad. And then you can calculate the inductance of fifth harmonic from tune formula 1 upon under root typically 2 pi into 50 into 10 into square. So it comes 85.76. Similarly for 7th it is calculated in the same way, applying the formula 61.4 and N11 19.62 millihenry microhenry, and the L13 is a 16.6 microhenry. Now numerical 10, solve numerical 3-phase AC transmission system having ascending end and receiving end voltage 400 kV and line reactance of 100 ohm. Calculate the current, power transfer and reactive power requirement. And so V1 V2 400 current you can calculate 2 into V delta by 2x and find 99619 kiloampere, and P V square of sin delta x 666.67 megawatt, and Q equal to V square 1 minus cos into 178.63 MVR. And these are the unsolved problems which you can solve. These are the references. Thank you very much.